Hi, everyone. I'm Chris Sommers from Keysight Technologies. This next talk is a comprehensive Sonic pins update. Presenting will be Reshma Sudarshan and Brian O'Connor from Intel, and Bhagat Janarthanan and Vamsi Punati from Google. Some of you might recall that at last year's workshop, Reshma co-presented on NDP transport using Sonic pins. Likewise, there were talks and demos about pins at last November's OCP Global Summit. I'm really looking forward to this update. Take it away, folks.
Thank you, Chris. Google has been a major user of SDN in the data center. We have seen that SDN leads to simpler traffic engineering as well as easier debugging. SDN also enables separation of control and data plane. We are able to run control plane in dedicated servers using high-end processors and compute optimal routes incredibly fast. And we continue to publish our findings on SDN. We have published papers on Jupyter, Orion to the industry. We have been working on the large-scale infrastructure. Recently, we have taken steps to grow SDN adoption both inside and outside Google. All right. Meanwhile, Sonic is becoming a mainstream operating system as well as open source. The modular container-based architecture of Sonic makes it highly scalable. Bringing SDN to Sonic allows the controller to manage switches seamlessly, as well as integrate into the data center infrastructure for both visualization as well as analytics. So we are excited to work on bringing SDN into Sonic. The P4 integrated network stack, or pins, starts with Sonic as the base framework. To enable SDN control of Sonic switch, we add support for P4 runtime, an open standard interface that enables runtime control of data plane objects. For configuration and telemetry, as well as operational support, pins relies on and enhances the Sonic EOMF project. This includes open config models, GNMI and GNOI, and provides a standard interface for configuration, telemetry, and control.
So next, I'd like to talk about the pins architecture and what we call the green path or the SI path. The pins architecture introduces a set of modules on top of the existing Sonic framework. As you can see in this diagram, the left side shows the existing Sonic modules. These are the boxes in white. On the right, starting from the top, we have an SDN controller, which is remote, meaning that it's deployed outside the switch. The SDN controller sends messages to the P4 runtime app over gRPC. Next, the P4 runtime app is a new local application running in its own container. It's responsible for translating the gRPC messages from the controller to the new P4RT tables that have been added to AppDB. The P4 orc has been added as part of orc agent and is deployed as part of the Swiss container. It reads the P4 entries from AppDB and translates them to SI entries that are written to ASICDB. From there, syncd and libsci are responsible for programming the data plane. You may be familiar with Sonic's synchronous mode, which is enabled by default. Briefly, when sync mode is enabled, the orc agent waits for a reply from syncd that says the operation was successful or failed. syncd also writes updates into the ASIC stateDB when entries have been installed. In pins, we're extending the synchronous reply capability to the application and SDN controller layers. When the P4 orc gets a reply from syncd, it passes along the success or failure to the P4RT app. It also writes the update into the newly created app stateDB. The P4 runtime app waits for the reply from P4 orc before completing the P4 runtime write request and replying to the SDN controller. The synchronous response path is important because the remote SDN controllers need immediate feedback to the intent that they publish. SDN controllers manage an entire fabric and have a view of the state across multiple switches. If one of the switches is not able to complete or accomplish a particular request, the controller is still capable of achieving the overall objective by using the other switches under its control. This is a common occurrence in SDN and a great advantage over traditional networking. That is, you have the capability to reroute traffic and create new flows around a misbehaving switch. Another advantage of the stateDB is that it can be used to expose the current state of the system at any time to applications in a format that is understandable by them. We believe that this will be a good mechanism in the future for other local apps as well. Next, let's look at some of the components in more detail. As we just mentioned, we're introducing a P4 runtime server in a new Docker container to Sonic. Multiple clients can connect to the server, and it can arbitrate between requests from different clients. The server also implements the set pipeline API, which allows the user to specify table fields. In the SCI pipeline, this allows changes to the ACL tables. The server also supports the read and write APIs. Write is how programming entries are added and removed from the various tables. Read returns the entire state of the tables, including counters if available. Clients can send packet outs, which will be admitted by the switch, and receive packet ins, which are packets that come from the data plane and have been copied or trapped to the CPU by the ASIC. The P4 ORC is a new component that translates between the app and ASIC DB entries. It's responsible for creating SCI objects and managing their reference counts. It also coordinates with other orcs for objects that are created by other applications, such as VRFs. The P4 ORC handles dependencies between SCI objects that are created in a batch. For example, we have to create the SCI next hop objects before we can create a SCI route that refers to them. The P4 ORC also listens to the response from syncd and passes the result along to the P4 runtime application, as well as writes the updated state to the app state DB. Let's take a look at a quick example to make this a little more real. First, the SDN controller sends a P4 runtime write request over gRPC to the P4 runtime server running in Sonic. In this case, the controller is sending a route entry. Next, the P4 runtime server translates the route entry and writes the result to appdb. Match fields are part of the key, and the action parameters are attributes. Next, the P4 ORC translates the appdb entry into SCI objects and writes them to ASICDB. syncd's reply is picked up by ORC agent, which then in turn sends the reply to the listening P4 runtime server and writes the new state to the ASIC state DB. The P4 runtime app completes the write request and sends the reply to the SDN controller. Now let's take a look at the status of the PINS project. The PINS MVP was released as part of the 2021-11 Sonic release last November. It includes a SCI program that supports layer 2 through layer 4 headers, an IPv4 and v6 routing table, and weighted cost multipath, or WCMP for short. Users can customize the pre and post routing ACLs as well as an egress ACL. And we have several SCI profiles that provide an example on how to do this. The PINS P4 runtime server supports read, write, packet IO, roles, and arbitration. It can also do port translation and provides basic validation of the P4 info that is sent by the controller. Looking at our roadmap, we have 3 things that are currently in progress, and we wanted to provide you with an update on some of those today. First is system level testing, which Vamsi will cover next. Next is the SCI generic extension path that Reshma will talk about. And the third is configuration of the P4 runtime application that will be presented to the Sonic community soon. There are also a number of opportunities for collaboration that Bhagat will cover at the end of this talk. Now I'd like to turn it over to Vamsi to talk about testing.
Thanks, Brian. In today's presentation, I'm going to talk about our test infrastructure that we use for PINS testing at Google. Yeah, move on. Yeah. Next slide, please. Yeah, so this is a standard test topology that we carry out all our functional testing that includes P4, data plane, control plane, and management plane functionalities. So as you can see in this picture, like the DET is connected to a control switch, which may be running pins or any other standard NOS, or DET can be connected to the traffic generator like XYarn for data plane and QoS testing. So the test framework, which provides GNMI, GNI P4 interface to talk to the DET, and it also provides interfaces to do operations like reboot and port state change on the control switch. And it also provides interfaces to the traffic generator to start and stop the traffic. So over the course of this project, like we developed tests using 2 different frameworks. So the first one is the ThinkIt. So it's a lightweight C++ library, and it's suited for data plane and control plane testing, and it has inbuilt traffic library for low rate traffic generation, and it has connectivity to the Axion traffic generator to do line rate testing and line rate traffic testing and QoS. And the test fixture in using this ThinkIt framework needs GNMI and P4 configurations of the DET, and it also needs to provide the connectivity information between the DET and control switch for the test to consume. And this is written in C++, and we have around like 100 tests, and the list is growing. And the second framework is OnData, and it is suited for running, developing and running the management plane and operational tests, and has got a rich set of features to support open config model testing. So it has got YGOT tools support, which basically translate the YAML files into the Go structs. And so this framework will take all the open config models as an API, as an input, and it provides get, set, and subscribe API support for all these models. And it also provides like the standard open config interfaces to the DET and control switch. And the tests also required to provide like GNMI configurations of the DET and control switch. And this is written in the Go, and we have about like 250 tests now, and this list is growing. So this is the ThinkIt on OnData. Instead of having two different frameworks, so we are planning to have a single framework to run all our tests that we developed in so far. So on the left-hand side, we have this OnData framework. So here, as you can see, the Go test and the test library functions, they talk to the OnData APIs, which in turn talk to the actual hardware through the bindings. So if someone wants to take this test and run them in their environment, they have to basically follow these few steps. First, they have to have their standard topology, the one that I showed in the first slide, like the DET is connected to the control switch, and they need to customize their bindings to their environment. So that include supporting their own reservation system bindings, and even the GNMI connections, like they may have specific changes they need to customize for their environment. In some cases, like the test infrastructure talk to the switches directly. In some cases, like they go through via proxy. So all the custom logic should be put into the binding support. And ThinkIt APIs would talk to OnData, and OnData in turn talks to the device, right? So likewise, like in ThinkIt APIs, now we are, as part of this integration, what we're doing is like ThinkIt APIs would talk to the OnData bindings, and the test run as it is. Like we don't have to do any changes in the test. The C++ test can run on this framework without any changes. So this is the status of the upstreaming. So the ThinkIt, the library and sample tests are already available in the Pins working group. And OnData as a framework, it's already upstream. And the last item is ThinkIt on OnData. This is work in progress. Currently, we are trying and testing things internally. And once it is ready, then we'll consider for upstreaming. Thanks.
Next, Reshma will be talking about the SCI generic extensions we've added for Pins.
Thank you, Brian. Pins started off as a standards-based open approach to bringing P4 and SDN into SONiC switches. This capability includes SDN-managed SCI objects, and the new capability I will talk about is the dynamic addition of SCI generic extension tables. This feature helps users when they want to extend an existing SCI feature or protocol or have proprietary IP in their applications that they want to write in a secure SONiC Pins environment. For example, congestion control mechanisms or DDoS prevention algorithms that need small changes in the pipeline and at the same time continue to have a uniform management interface of SONiC across their applications and devices in their networks. Users of SCI generic extensions assume the underlying SCI pipeline as the baseline and intend to create few new tables as touch points to extend SCI features. To add a couple of generic extension tables in a couple of places in the pipeline, and they're programmed in a manner that is independent of the data path. These tables could change the metadata that is used by the pipeline, or they could create new metadata that is not used by the pipeline's regular flow. Broadband Network Gateway is another example application which can be a candidate for using PIN's SciGeneric extensions, as it needs a double VLAN tag decap and map it to the subscriber ID and be able to do metering. Features like DDoS need more frequent updates, and hence the traditional model do not always work. SciGeneric extensions allows prompt and swift modifications, network modifications that help with applications like DDoS mitigation. In keeping with the SONiC methodology, realizing SDN through creation of application and agent layers to implement network configurations from the controller through P4 runtime APIs, the P4 org agents is a new component. Org agent is a new component that PINs introduced in SONiC and is part of the org agent process as Brian described. While the P4 runtime server application receives the controller messages in the form of gRPC writes and converts them into application DB-P4 RT table entries, the P4 org agent process manages its own table in the application DB with the P4 runtime prefix and translate these entries into corresponding ASIC DB. The SciGeneric extensions will extend the P4 org agent to add a generic handler for managing the non-Sci objects. Our main objective is to ensure object sharing and cross-referencing of SciGeneric objects is supported. As P4RT interface requires response of each programming request to match with real hardware state, synchronous mode between org agent and syncd is enabled. P4 org agent implements notification channel to send the response further up to the P4RT application for SciGeneric extension objects as well. Response is marked in the application state DB, and Sci API success call written into ASIC DB and propagated to org agent and the application state DB as well, which propagates this to the client at the end. From ecosystem perspective, making Sci changes requires changes in all levels of stack, and SciGeneric programmable object is generic enough to provide the essential metadata passed as part of the CRUD API to support new table additions that the user wants to add into the hardware. In PINs, it is possible for user to model the entire Sci pipeline, and these specific behaviors in P4 push them down to the device as part of the initialization and control these entries at runtime. The SciGeneric object passes the object type along with the value and is adding when it is adding the match action, action keys and action parameters to the Sci layer for easy and complete interpretation of ASIC DB entry in order to program the hardware. At Intel, we are working on a soft switch running SONiC stack on a server using the P4 DPDK pipeline, which is P4 programmable DPDK backend, and is performant. It also adheres to the latest PNA standard. It's a good vehicle for left shift and development and helps get the framework all ready, and with P4 DPDK using the same software stack for soft switch as well as hardware. So it is possible for us to run PINs with SONiC on the host.
Now let's look into the future challenges and opportunities in PINs. As you heard from Brian, one of the first visions was the green path. We have now executed that vision. We have PINs running on multiple ASIC vendors and system partners. We are able to use that and demonstrate in various proof of concepts. Next, the red path is something that we are working on now. As Reshma mentioned, this is something that we would like to accelerate and accomplish in the near future. We would also like to strengthen the testing methodologies. We heard from Vamsi about the new tests and the amazing test frameworks that we are developing at Google. We are working on upstreaming this capability to the community. Looking ahead, we are challenging ourselves, and we have started to look for the next phases for PINs. One area that we have been looking is the introduction of PINs to chassis. Currently, SONiC supports a disaggregated architecture for chassis. This means there's a stack per ASIC. The BGP instance is running on the chassis are connected to each other through iBGP sessions and exchange information between them. Introducing a controller to this chassis brings a few different options. The P4 runtime server could be present in each line card along with the remaining stack, or it could be centralized. Both options are possible. A centralized P4 runtime would make it convenient for a controller point of view. And we are looking at both options here. Another equally important aspect is to be able to simulate the switch. We have very few options to do this effectively today. On this front, we're keenly looking forward to the P4 DPDK becoming a possible solution. PINS is open for collaboration and new ideas. PINS is at the intersection of multiple communities and is growing through an exciting growth phase. Please join us in the PIN subgroup from Sonic for discussions and collaborations. Thank you.
Great presentation, guys. You guys have done a lot in the last year. It's a huge amount of plumbing. I've worked in middleware for a couple decades, and I can appreciate fitting all those pieces together and making changes and moving forward is really a challenge. And since I've been following this PINS project for last year, I've been impressed with the kind of the audacity and courage of going in and doing this kind of melding of two sort of different DNAs and making it work. So hats off to everyone involved. I like to think it's like taking an apple tree and grafting an orange tree onto it or something. It's not straight biology, it's tricky stuff. So I have a few questions. One is, who might adopt PINS besides Google? So far, Google seems to be the kind of cloud service provider that's spearheading this along with the community. Who might else like to use it?
I'll take this question. As we talk to customers, and particularly when we talk to COSPs, I see that applications such as SRv6 and SRv6 proxy really need those data plane changes that they're very much interested in using PINS for. While using the local control plane for traditional routing, they would like to use PINS, especially with side-generic extensions, for additional changes in the data plane. When we look at 5G applications at the far edge, there are changes that they would like to write for the 5G applications that requires, again, PINS for the data plane changes, while the near edge and core, the rest of the network continues to use BGP, VPN, VXLAN, for example. So definitely there are lots of use cases, and in the future discussions, we can elaborate on even more, but a lot of applications and interest in the industry.
Oh, thank you. That's encouraging. So, question about testing. There's two frameworks you presented, and there's even a potential kind of integration with them. That would be ThinKit and Ondatra. Can you explain why two different frameworks were adopted? And what's the rationale behind that?
Sure. Yeah, I'll take that question. So what happened was, like, even before the PINS was formally launched at Google, right? So the team was doing some P4 testing, and they created a small framework, like where the test framework is talking to the switch through P4 interface. But once the PINS was formally launched, they extended the same work frame to add like GNMI and GNOI interfaces, and created a ThinKit. It's named as a ThinKit framework. Even though ThinKit is a very lightweighted and designed with the intention to upstreamability and all that stuff, but somehow while developing the tests on it, like for testing the management plane, writing tests to cover all these open config models, the team felt like it's not a good fit. Basically, what happens with the ThinKit tests, the test developer using the ThinKit framework is the user has to create complete GNMI request with the open config payload and with the path and the payload. And once the response is received, they have to do a lot of validations and parse the information and all that stuff, right? So they were thinking how to make the whole exercise easier. So they were investigating different frameworks, and then we realized the Ondatra is already developed with the intention to support this open config model testing. So, and with Ondatra, we have got YGOT tool support. So basically, it takes all these open config models as input and and generate ready-made APIs which can be used in the test development. So that really is helpful, and team find it quite easy to write test cases using this framework. So that's how we started adopting on.RA for management plane testing. So that's how we ended up having 2 frameworks. Now going forward, we want to have think it running over on.RA is a model that we want to go forward and give this to open community.
Oh, okay. Well, thanks. That makes a lot of sense.
Mm-hmm.
So community-wise, you put out like a call to action. What kinds of concrete tasks would you like the community to contribute?
I can take this one. There's a spectrum, I guess, as with any open source project in any community. But the easiest way to start to get involved is just try this out. We've got a pins getting started tutorial as part of this workshop that you can download. You can experiment with on your own hardware. You can try out simple CLI clients or SDN controller like Onos, and just see how it works, if it works, and give us feedback. Once you get it running and start building cool apps, we'd be really interested in hearing about them, and taking some of the requirements that your applications have and bring to the table to the pin stack. And then obviously, we're always looking for new development partners. So if you want to send pull requests or add new features or capabilities or make this better in some way, we definitely accept pull requests. So kind of a standard canned open source answer, but hopefully the tutorial is a good place to get started, and certainly send us feedback. We'd be really interested in hearing about what you're working on.
Great. Well, thanks a lot, everybody. That was a great presentation, and I look forward to following the future progress of this project.
Thank you, Chris.
Thank you
for moderating it.